exponential chaotification. This is the topic of our video. Okay, it's about chaotification, and we are presenting the results of a recent work of ours with my colleague Marcin. Okay, multi-composition exponential modulo chaotification model. Okay, big words, but I will explain everything. It's published in Chaos. I will put a link for downloading the paper in the description of the video. Okay. So we are dealing, as we can understand, with chaotification. I have many videos on the topic because I have been studying chaotification for the last couple of years. Okay. Let me remind everybody, if you haven't seen the other videos, chaotification is all about taking any possible seed map from the literature, sign map, logistic map, Chebyshev map, sign modulo, sign exponential, any map that is already published, okay, combining it with another function, of course, the architecture of this function we design ourselves, and the goal is basically to generate richer chaotic behavior. Of course, when I say richer chaotic behavior, what do I mean? Depends on the problem at hand. We may generally want to achieve higher Lyapunov exponents, more complex chaotic behaviors, I mean, transitioning in and out of chaos. We may want to achieve robust chaos. Personally, I'm very interested in that. Okay. We may want to control the mapping domain for the solution time series. Okay. We may want to achieve hidden attractors. This is basically the case of chaotic maps that don't have any equilibria. Remember, equilibria are also called fixed points. Okay. So all are all many different problems when dealing with chaotification. What we did here, we designed the chaotification technique with a very, very interesting structure. Okay, outside it has a modulo function. Okay, the modulo basically bounds the mapping domain between 0 and 1. Okay, and inside, that's why we call it multi-composition, because we have the composition of multiple different functions. Okay, and all of these functions have the same structure. Each of these calligraphic f function is an exponential term, so we have exponential of f. F is any seed function, okay, minus one parameter alpha plus one parameter b, okay. So a and b parameters are real values. They basically work as offset boosting parameters, either for the exponential term or for the whole function, okay. So one parameter is on the exponential power, the other is outside, okay. F is any seed function. You can take the logistic map, the sign map, any map from the literature. Okay. So each calligraphic F has an exponential of a seed plus some stable parameter. And we have composition of multiple such functions. So we have composition of functions and overall modulo 1. So that's why we call it, okay, multi-composition exponential modulo chaotification. Now remember, in chaotification it's very important to try and provide some mathematical results for your developments, okay? Because there are many papers in chaotification in the literature. Unfortunately, some of them don't have mathematical results. As you can understand, a mathematical result is much, much, much stronger than a simple experimental result, okay? So one of the first things we did is provide a formula for the Lyapunov exponent for this family, which is of course very complex. I should mention that the Lyapunov exponent overall depends on each individual f calligraphic function, but also depends on the derivative of the seed functions, okay, f. So this is a very, very interesting result, okay. Overall, we can say that the seed function can be a single function so that we cannot overcomplicate things, but we can have different seed functions, of course. Now, for this very general family of map, which basically has a lot of, how can I say this, a lot of design freedom. Okay, you can change the number of compositions, you can change the parameters, you can change the seed function. Okay, in the paper, I'm going to show you only the most important results. We propose three families of maps. One of them is the simplest one. It's the modulo exponential. It has a simple exponential function. Okay. Here, we again have some analytical results for the Lyapunov exponent formula, which actually depends on the mean value for the solution of the time series. And also we provide some conditions under which this map can achieve no equilibria and chaos at the same time. Okay, here you see a cobweb diagram. The map clearly has no equilibria, no fixed points, okay, and it also has chaotic behavior. So this is very, very interesting because it's among the first works, some of them also previous works developed by us, where we try to simultaneously achieve two things, robust chaos and absence of equilibrium, which is very, very cool result. Okay. This is the diagram of Lyapunov exponents. Okay, you see that as A increases, we fall out of chaos, but for smaller values, we actually have very large and very wide regions where chaos appears. So we do have robust chaos here. And we also have a study for the equilibria of the map and where do they appear and reappear and where do we have hidden attractors basically, but I'm not going to show you that. I'm only showing you a couple of results. The second family of maps has basically what we call super exponential terms. Okay, so it has a composition of exponential to the x. Okay, this helps achieving a very high Lyapunov exponent value. Again, we have some analytical results for the Lyapunov exponent and for the absence of equilibria. And for this family as well, we can achieve, as you can see on the right here, chaotic behavior without equilibria. You can see that the phase diagram doesn't intersect the bisector. Even more importantly, here we have a very wide region of robust chaos. Here you can see the Lyapunov exponent as we change two parameters. No black at all. Black means periodicity. Here we don't have any black color. So basically we have chaos through and through for this family. So robust chaos for a very wide parametric, basically for a very wide, parametric range. And the third family, which is a combination of exponential to the exponential with the sign map. Okay, that's why you see here e to the k sine pi, which, as you know, if you follow chaotic theory and chaotic systems, that this is a sign map. We have some Lyapunov exponent results here. Unfortunately, although we do derive some conditions for the absence of equilibria, here we couldn't find any parameters that give absence of equilibria. But as with the previous map, you can see on the right here, we do manage to get, I hope I'm not blocking the view, we do manage to get, again, robust chaos. Okay, this is the Lyapunov exponent, and this is positive everywhere for a very wide parametric region. Okay, so basically all three maps have very good robust chaos properties. And of course, you can design many more families of chaotic maps using different seed functions, different number of compositions. You can go nuts basically and define many, many different families of maps. Okay, but we only propose three families here because, okay, the paper cannot be like 50 pages long. And to also study the applicability of these maps in some sort of application, what we did is we took a pseudo-random bit generator from a previous paper of ours in IEEE Access. You can see it on the left, it's open access. So we did the random bit generator from this paper and tested our three chaotic maps in this generator using the NIST tests. Okay, the classic ones, if you are familiar with PRBGs, they're very classic statistical tests. All of the three chaotic maps give random bit series that actually manage to pass the NIST statistical testing. Okay, you can see the table here. I hope I'm not blocking the view. Actually, all three maps give positive NIST results. This is a very good result because it means that if we use these maps in a chaotic bit generator, we can actually manage to get statistically random bit series. Okay, very, very nice result, very interesting result. In this paper, we actually test many, many different chaotic maps. Not all of them pass statistical testing, but the three we propose here in this paper, they actually do pass statistical testing. So some observations overall, we managed to provide analytical formulas for the Lyapunov exponent and some conditions for the absence of fixed points, okay, for the three families that we had. If you study the increase of the key space compared to the seed function, indeed, we managed to achieve a much, much higher key space. So this is a very, very nice result. We managed to achieve robust chaos, which is again a very positive result for chaotification and an absence of fixed points. Okay. Another important part is that, of course, the maps that we considered are acceptable seeds in a bit generator. And also, it's very important to note the architecture that we have designed, which is a combination of different exponential type functions, has a very high amount of generalizability. So you can play a lot with this family and design many different variations using different amounts of compositions Okay, different parameter values and different seed functions. So you can play a lot and define many different map families that are based in this sort of exponential codification. Okay. Now, for the future, this is of course one of the first things that I suggest studying. Okay, different seed functions. We consider the exponential and linear and the sign map, but we can consider other types of polynomial, trigonometric, piecewise functions. Okay, a lot of variations to study. Another extension is to consider multi-dimensional, that's why I say ND, like two-dimensional, three-dimensional versions of this codification. I'm assuming you're gonna achieve robust chaos here as well, maybe even easier to achieve robust chaos in higher dimensions. Okay. One difficult study is, of course, the problem of identification using techniques like sparse identification, SINDI, a very well-known technique. I don't know how well they would work with this map because it is very complex, but it's an interesting problem of study. And another very interesting problem to consider in the future is basically the whole problem of chaotification and the fractional version of this family of maps, especially in combination with no equilibrium maps. For example, study how the fractional version of this map will change and how the problem of achieving no equilibrium maps will change under a fractional version of this map, and how much does, changing the fractional degree will affect or not affect, I'm not sure, I don't have any idea at the moment, the appearance of no appearance of equilibrium. Okay, this is a very interesting problem. I don't study fractional systems, but I'm generally interested in them. I follow publications on fractional systems. This is gonna be a very interesting problem for the future. Okay, so overall, I'm gonna put a link into the description of the video for reading this paper. I believe if you work on chaos theory and codification, you will find it very interesting and helpful. Okay, if you have any problems or any questions, write them down in the comments, and thank you very much.